Welcome. You ever flip a light switch and just wonder what actually happens in that split second? Well, today we're going to pull back the curtain on that invisible force that powers pretty much everything in our world: current electricity.
It honestly feels like magic, doesn't it? One little flick and boom, a dark room is suddenly full of light. But it's not magic, it's a perfectly controlled, completely invisible flow of energy. So, let's dive in and see how it all works.
All right, here's our game plan. We'll start with the basics. You know, what electricity even is. Then we'll get into the forces that control it. After that, we'll uncover its one golden rule, see the two main ways it's all put together, and then we'll connect everything right back to that bill you get in the mail. Okay, first things first. Let's tackle the most fundamental question. What is electric current? What is actually zipping through all those wires?
At its core, electric current is just charge that's on the move. That's it. We measure how much charge, which we call Q, flows past a certain point over a specific amount of time. And the unit we use to measure this flow is the ampere, or you'll usually just hear it called an amp.
Now, probably the best way to get your head around this is to think of electricity like water flowing through a pipe. It's a classic analogy for a reason. So if electricity is the water, then the current, well, that's just how fast the water is moving. So just to be clear, you've got two key players here. You have the actual stuff that's flowing, which is the charge, and then you have the rate at which it's flowing, that's the current. It's kind of like the difference between the water itself and the speed of the river. Okay, so this charge is flowing, but why? What gets it moving in the first place? And on the flip side, what can slow it down? Turns out it's all about two competing forces. You can think of it like a constant tug of war happening inside every single electrical wire. There's a push trying to make things go, and a squeeze trying to hold things back. Understanding this little battle is the key to, well, everything in electricity.
So let's talk about the push. Its official name is potential difference, but everybody just calls it voltage. Going back to our water pipes, voltage is basically the water pressure. The more pressure you have, the more powerful the push, and the faster the water is going to want to move.
And fighting against that push, you've got the squeeze. We call that resistance. In our pipe analogy, resistance is like a narrow spot in the pipe, or maybe it's clogged with some gunk. It literally squeezes the flow, making it way harder for the charge, our water, to get through.
Now here's where it gets really, really cool. These three things we've been talking about, the flow, the push, and the squeeze, they aren't random. They're all connected by one beautifully simple rule. Back in the 1800s, this German physicist, Georg Ohm, he figured it all out, and his discovery, this simple relationship, became the absolute cornerstone of how we understand and build electrical circuits today. And there it is, Ohm's law. It looks so simple, but it is incredibly powerful. For most basic circuits, this is the golden rule. Voltage equals current times resistance.
And if you think about it, this formula just makes perfect sense, right? It tells us that the flow you get, the current, goes up if you increase the push, the voltage. Push harder, you get more flow. And it tells us the flow goes down if you increase the squeeze, the resistance. Squeeze the pipe more, you get less flow. See? It's totally intuitive.
All right, so now that we have the rules of the road with Ohm's law, how do we actually put this stuff together? Well, when you're building a circuit, there are really only two fundamental ways to connect things. This table really breaks it down nicely. In a series circuit, everything is on a single one-lane road. The current has no choice but to go through every single component. But in a parallel circuit, the road splits. The current can take multiple paths. This is a huge deal, and it's exactly why your house is wired in parallel, so you can turn on the TV without having to turn on every other light in the room.
Okay, time to bring this all back to the real world. How does all this theory about flow and push and squeeze connect to the coffee maker, the laptop, the things we use every single day, and maybe more importantly, the money we pay for them?
Let's talk about power. You see the word watts on pretty much every appliance. Well, power is just how fast something uses energy. It's the push, voltage, multiplied by the flow, current. So a 100-watt light bulb is just burning through energy faster than a 60-watt bulb, and that's why it shines brighter. But here's the catch. Your electric company doesn't bill you for how fast you use energy. They bill you for how much energy you use in total. That's electrical energy, and it's simply the power of a device multiplied by how long you leave it running. A tiny nightlight left on all month could easily use more energy than a super powerful microwave that you only use for a couple of minutes a day.
Now, in a physics lab, you'd measure energy in joules, but a joule is an incredibly tiny amount of energy. Seriously, if your electric company billed you in joules, your bill would have so many zeros it would look like an astronomy textbook. So, for practical purposes, they use a much bigger unit, the kilowatt hour.
And get this, just one of those little kilowatt-hour units that you see on your bill is equal to a whopping 3.6 million joules. It really puts into perspective the massive amount of energy we're dealing with every day. So let's put it all together. Think about a powerful 2,000-watt hairdryer. Well, 2,000 watts is just 2 kilowatts. If you run that thing for 30 minutes, half an hour, you've used exactly 1 kilowatt-hour of energy. And just like that, you can look at the watt rating on any appliance in your home and figure out not just how it works, but what it's actually costing you to run. Now that's powerful stuff.